Now coming to the physical properties of alcohols. Alcohols are associated due to hydrogen bonding because there is an OH group in alcohol. Then the hydrogen bonding in alcohols are lower in number than that in water because of the presence of alkyl group which cannot form a hydrogen bond. Now, as in the case of hydrocarbons, the branched compounds have low boiling points. This is because due to branching, the molecule assumes a coiled conformation, just like a coil which is having a nearly spherical shape, and for any geometric object, a sphere has a lower surface area than any other object, say cube having same volume, and so due to lower surface area, the van der Waals force of attraction between branched compounds will be lower, and hence association of molecules will be lower. Hence branched compounds have low boiling points compared to normal compounds. Here normal propyl alcohol boiling point 97, whereas isopropyl alcohol having a branch so this is a branch. Boiling point is 82.5, and N-butyl alcohol boiling point 118, whereas isobutyl alcohol is shown with a branch, a methyl group is a branch. Boiling point reduces to 108, and for tertiary butyl alcohol, where the carbon bears 3 methyl groups, so that there are 2 branches. So this may be considered as a branch when this is a straight chain heterocarbon. So there is only one branch here. So there is only one branch, and it is having a coiled conformation nearly equal to the shape of a sphere, the lower surface area, and hence boiling point is further reduced to 83 degrees Celsius. So in any family of compounds, branching reduces the boiling point due to a reduction in the surface area of the molecule. Now coming to solubility, the lower members like methanol, that is methyl alcohol, and ethanol, that is ethyl alcohol, are soluble in water due to hydrogen bonding. Now the polarity, dipole moment of water is 1.84, and that of methanol is 1.70, and that of ethanol is again nearly equal to that of methanol, that is 1.69 for ethanol, ethyl alcohol. So that the delta negative charge over oxygen atom in methanol and delta negative charge over oxygen atom in water. So there will be delta positive over hydrogen, and there will be delta positive over this hydrogen, and again a delta dash positive over this methyl group. Anyway, the total positive charge, the magnitude of the total positive charge here will be equal to the magnitude of delta negative. So the partial negative charge over oxygen and partial negative charge over oxygen in water and that in methanol. Now here the partial negative charge or oxygen in methanol is found to be less than that in water. So oxygen in water carries a greater amount of partial negative charge. So water is more polar than methanol. So that hydrogen bonding between methanol and water, as shown here, ROH bonded to HOH bonded to HOR. It is called AB attraction. Here A is methanol and B is water. So between methanol and water and between methanol and methanol, it is called AA attraction. The strength of hydrogen bond will be higher in the case of AB attraction because water is more polar. So stronger hydrogen bond is formed between methanol and water than between two methanol molecules because of the polarity of the OH bonds in both these compounds. So greater the magnitude of negative charge, and the greater will be the magnitude of positive charge over hydrogen, and so stronger will be the hydrogen bond. And here A attraction and AB attraction, when we compare, AB attraction is greater in the case of methanol and ethanol, so they are soluble. When the alkyl group becomes larger, bigger in size, so that the alkyl group contain a greater number of carbon atoms, higher alcohols we say, they contain larger alkyl groups, then the van der Waals attraction between these alkyl groups become important. So for higher alcohols, the van der Waals attraction is important because the alkyl group is larger in size, and larger the size of the alkyl group, larger will be the surface area, and larger the surface area, larger will be the van der Waals forces between groups. So in larger alcohols, both hydrogen bonding and van der Waals forces of attraction are important. But when larger alcohols come into contact with water, water cannot form a van der Waals bond with the alkyl group because water prefers hydrogen bonding. Since alkyl group cannot form hydrogen bond with water, and larger alkyl groups are attracting each other by van der Waals force of attraction, the attraction between alcohol molecules will be higher than the attraction between alcohol and water molecules. So larger the alkyl group, higher will be the size of the alkyl group, higher will be the surface area, and higher will be the attraction between alkyl groups in the alcohol. But when we come to the case of AB interaction, that is interaction between alcohol and water, since water is reluctant to form van der Waals bonds because it prefers the more stronger hydrogen bonds, and alkyl group cannot form hydrogen bonds, the solubility of higher alcohols in water cannot be observed, or it is not possible for higher alcohols to get dissolved in water. Now coming to the chemical properties. Alcohols are acidic, but they are not so acidic as water. This is because in an alcohol, the alkyl group shows a plus I effect. Now this plus I effect of alkyl group increases the electron density over oxygen, and so this oxygen becomes reluctant to absorb the pair of electron in the OH bond. So OH bond electron pair is not easily absorbed by oxygen when the alkyl group is showing plus I effect. So removal of H as H positive is made difficult when the alkyl group is showing plus I effect or increasing the electron density over oxygen. So when the electron density over oxygen atom is increased, it will not strongly hold the electrons in the OH bond towards itself, and removal of H positive is made difficult by this process. So alcohols are less acidic than water. And one acidic reaction of alcohol is that reaction between sodium and ethyl alcohol shown here. Now metal and acid can react to form salt and hydrogen. So CH3CH2OH plus Na, CH3CH2OH splits into CH3CH2O negative and H positive. H positive absorbs electron of sodium, so that sodium is left as Na positive, and H positive absorbing electron from sodium is converted to hydrogen atom. Now two such hydrogen atoms combine to form hydrogen gas, and the salt formed is sodium ethoxide because the alkyl part is ethyl part. And just like sodium hydroxide, we say sodium ethoxide, sodium ethoxide, the product. So that shows the acidic reaction of alcohols. And the acidic nature of alcohols is decreased by increasing the substitution at alpha carbon. Alpha carbon is the carbon to which OH group is connected. So when there are more alkyl groups on alpha carbon, the acidity of alcohol is decreased. This is because greater the plus I effect of alkyl groups, greater will be the electron density over oxygen atom in the OH group, and greater will be the reluctance of oxygen to take up the electron pair in the OH bond. So a primary alcohol with only one alkyl group is more acidic than a secondary alcohol with two alkyl groups showing an increased plus I effect of two alkyl groups. And then when we come to a tertiary alcohol, there are three alkyl groups, so twice the inductive effect of a primary alcohol. Then greater plus I effect of alkyl groups, so that greater will be the electron density over oxygen in tertiary alcohol compared to primary and secondary, so that the electron pair in the OH bond will not be easily taken up by oxygen atom. So tertiary alcohol shows the least acidity, and primary alcohol shows most acidity, and again water is more acidic than all the types of alcohols. So alcohols are weaker acids than water due to plus effect of alkyl groups in alcohols. Now a second reaction, that is formation of esters. Now esters contain the divalent group C double bond O and valency. So two valencies over carbon and oxygen, that is a carbonyl group, that is ester group. Now esters are formed by reaction between an acid or derivative of acid and an alcohol. See, a free acid like acetic acid can be used, or a derivative of this acid. This is called acetic anhydride. Acetic See, acetic anhydride is obtained when acetic acid is treated with phosphorus pentoxide, which is a dehydrating agent. Now, two molecules of acetic acid react eliminating a molecule of water. So, two molecules of acetic acid remove an HOH and then combine to form CH3CO or COCH3. Now, that is acetic anhydride. Now, this compound is easily hydrolyzed to acetic acid, means it can chemically react with a molecule of water, and an HOH molecule will split as H positive and OH negative, and this O negative will combine with H positive, and the C positive will combine with OH negative, so that we get CH3COOH and CH3COOH. So hydrolysis can occur to acetic anhydride producing acetic acid. So that acetic acid anhydride is the dehydration product of acetic acid obtained by heating acetic acid over phosphorus pentoxide. Leave it. Now, reaction between acetic anhydride and ethanol is catalyzed by acid, and we remove a molecule of CH3COOH, so that CH3CO portion is getting connected to C2H5. We get ethyl acetate, CH3COO, C2H5. Now, with acetic acid, the OH group of the acid is getting removed, not the OH group of alcohol. The OH group of acid and H of alcohol is getting removed as a molecule of water. Reactions are reversible in both cases. We get ethyl acetate and water, and its reactions are catalyzed by acids. Now, the reaction between acid chloride and alcohol is catalyzed by a base called pyridine, PYRIDINE, pyridine. Now, pyridine is a compound similar to benzene, and benzene is this structure. All positions contain CH groups. Now, remove one CH group and place one nitrogen there. So, carbon has 6 electrons and hydrogen has only 1 electron. So, CH group has 6 plus 1, that is 7 electrons, and nitrogen also has 7 electrons. So, pyridine and benzene are having similarities. Now, there is a lone pair over nitrogen, and a species, a molecule which can donate a lone pair to H positive is called a base. So, pyridine is an organic molecule and basic, so it can be used as an organic base. And there, an acid chloride is having the group COCl. So, any acid chloride is represented as RCOCl. Now, R is an alkyl group. Here we take CH3COCl, that is called acetyl chloride. Now, it can be obtained by the reaction between acetic acid CH3COOH and PCl5, just like the replacement of OH group in alcohol, ROH giving RCl. This OH may be replaced by Cl, we get CH3 COCl. So reaction similar to alcohol. The OH group is replaced in acid by chlorine using PCl5. Just like the reaction between ROH and PCl5 to give RCl. Now acetyl chloride reacts with ethyl alcohol, and here a molecule of HCl is removed so that this pyridine can react with HCl producing the salt, where the lone pair of nitrogen is donated to H positive. We get the corresponding positive charge over nitrogen, and this is called a pyridinium chloride or pyridine hydrochloride it's called, and we get CH3CO or C2H5 and HCl. So much reactions. Now we will see further reactions later. Thank you.